So, what we have seen in the previous class was that the variation of shear force and variation of bending moment along the length of the vessel. Now, the two curves which we try to draw, I have just given a small example here. SF depicts the shear force diagram and M curve depicts the bending moment diagram. Now, what we can see from these two diagrams, that the shear force is 0 at the after perpendicular, that means at the after end, also at the forward end, and somewhere near the midship region. And the bending moment is 0 at the two ends and is maximum somewhere near the midship, where basically the 0 shear force in the beam is occurring. From the mathematical point of view also, this satisfies this condition. And the maximum shear force which we can see, either positive or negative, is somewhere near L by 4 from the ends. Now, these conditions fulfill our basic boundary conditions, because when the ship is floating in water, the two ends are free, and therefore we say that a ship girder is floating in water in free condition. Ends are free. How it flexes is a different thing. So, when it flexes, basically there will be some nodes one can perceive which will be away from the two ends, and somewhere there the 0 displacements will be there. That we will try to say it in a more details when we will try to do something about the ship vibration. Okay. So, here we have a maximum value of SF, here we have another maximum value. Out of the two, one will be absolute maximum, and somewhere here we have the maximum value for the bending moment. Now, what are we going to do with these maximum values? Just knowing a particular figure and its position does not satisfy our condition, our requirement, we do not know what to do with them. So, basically the maximum shear force, we should relate it to the maximum shear stress in the material, and the maximum bending moment should be related to the maximum bending stress in the material. Now, these stress values, we understand that they are something as the ultimate strength of that material. So, if it crosses a particular limit, then we say that the material may not behave in a manner which we would like it to behave. Say for example, if we consider the elastic behavior of the hull girder or the equipment, and if it crosses the elastic limit and goes to the plastic limit, then that behavior is not acceptable to us. That means when the load is removed from the structure, it will have a permanent deformation, which we do not want. So, we specify that maximum limit depending on the material which we are using for the hull girder. Now, there is another thing, that there are many forces which we cannot foresee, or we are not in a position to either understand the mechanism or evaluate them in a proper manner. If that is the case, then we have to give some margin to this value, and that margin, which is because of the uncertainty in the behavior, uncertainty in the forces, uncertainty in our calculation procedure, whatever you call it, can be a cumulative effect, or they may try to cancel each other. It can be either way. Now, we do not know, and therefore, we have to be slightly on the safer side, and to take into account this safety, we say that we apply a factor of safety to the material stress limit. In fact, this is nothing to do with the loading factor. Many a times people say that you have taken a factor of safety of 2, that means whatever load you have considered for the design, you can load it twice that amount without failure. It is not so. We have taken it 2 because the other 50%, I am not sure whether that load is going to be there or not. So, I am keeping a margin for some unforeseen circumstances. Okay. So, factor of safety is put, and we say that we have a permissible stress level. Now, this permissible stress level can be calculated on the basis of the elastic limit, on the basis of the plastic limit, whatever the case may be. Nowadays people are going for ultimate failure analysis, and on that basis they try to specify what is the factor of safety. Okay. So, basically after obtaining this curve, we are interested to find out what is the maximum stress generated in the structure somewhere and see whether that is within the permissible limit or not. Now, as we can see, the shear force is maximum at these 2 points, and therefore somewhere here in this section the shear force will be maximum. On the other hand, the bending moment is somewhere here maximum, and the position is where the maximum bending stress occurs, there the shear stress is 0. So, there are 2 different locations, and at these 2 different locations one has to see that those sections are safer from shear stress and from the bending stress point of view. Now, let me write down what is the expression for the bending stress. Sigma bending, sigma is the notation we use, is nothing but the bending moment maximum, I take M max, and section modulus minimum. Now, this is the geometrical property of the structure. We will talk about this section modulus in more details when we will take it up, but what is section modulus is basically I of the material, that is second moment of area about its neutral axis, so we call it INA, divided by the skin distance where I am trying to evaluate the stress, so I by y. Now, when we try to find out what is the shear stress is the shear force we are taking maximum divided by all that area which participate in taking up the shear force. So, we say area in shear. It has been found that all vertical cross sectional, all the vertical material participate in the shear stress. The horizontal members in that particular section for this particular case will not be effective for the shear taking load. So, that means when we take a particular cross section, then wherever we have the webs, suppose you are having a longitudinal there in the form of a T section, then it is the, let me draw it, then it is this vertical member of the web which will participate in taking the shear load, not the flange of this. Okay. And therefore, we also try to say, or we will try to find it out now, that shear stress is a position dependent within the section. Like in bending moment, we can say that as y increases, I by y will decrease, because the cross sectional second moment of area is constant, the material is constant, and therefore I, that geometrical property, is constant, but the y near the neutral axis is 0, and there we have 0 stress value, bending stress. That is why it is neutral, because there is no stress. And when you go away from that place, y increases, your z also increases, or the section modulus decreases. So, M maximum divided by, you have a minimum section modulus which gives you the maximum stress. And the variation is linear because y is a linear function of the depth. Okay. Now, here we will find that at the two skins, that is the deck part and the keel part, the shear stress value will be 0, but it will become maximum near the neutral axis. But if we are trying to find out shear force maximum divided by the area in shear, what we get is shear stress average. Okay. I will come back to the bending moment or the bending stress once again. Let us take a typical cross section of a ship. This is the center line, this is the bottom I have drawn. We can have an inner bottom here, you have a center girder here, somewhere here is the side girder, and we can have some deck girders here, and then we are having longitudinals in the deck. Longitudinals in the inner bottom, longitudinals in the outer bottom. In this particular location there may be a web frame, or maybe every third frame there is a web frame or some such thing, that the rule governs that the distance between the two web frames need not be should not be more than 3.2 meters or some such thing. Now, when we are trying to find out I, this I is of the material sections which are continuously extending from one end to the other end, or for the major part. Normally we consider that from the after peak bulkhead to the fore peak bulkhead, in that region, or if we want to take the superstructure, which by definition is extending from side to side, and the extent is not less than 40% of the length. So that will contribute towards the longitudinal strength. All these members we try to find out what is the second moment of area. So this neutral axis will be somewhere here, and I of this section has to be calculated, and then we say that the Y value for the deck, it is here, and for the keel this is this value. Now when the ship undergoes, say, hogging or bend or sagging bending moment, if we take the hogging condition, then the deck is under tension and the keel is under compression. It is in hogged condition, and therefore the deck stress which is in tension and the keel stress which is in compression will have two different values, and what we can write is sigma for the deck, sigma for the deck is M max by INA divided by Y deck, and sigma for the keel will be M max divided by INA, the same, I by Y of the keel value. Now here we can see that the I by Y for the keel will be numerically greater than I by Y for the deck, because this neutral axis, by virtue of the materials, the way it has been dispositioned, this neutral axis will be slightly more than half the depth of the vessel from deck side. That means YD is greater than D by 2 and YK is less than D by 2. And by virtue of that, the numerical value of I by Y for the deck will be lower than I by Y for the keel value. And therefore, the stress at the keel will be somewhat lower than the numerical value at stress at the deck level. Okay. This is the reason why people say that when you have a superstructure, by definition a superstructure which is 40% length or more, extending from side to side, should be avoided in a ship, because that number of tiers will add on to this YD. If you have some superstructure here extending, let me draw it with a different color. Suppose I add 3 tiers here. This will virtually raise this neutral axis position also. But what happens? This value will be far greater than this value here, and this will drastically reduce the permissible stress there, or it will increase the stress at this level, which will become dangerous for the health of the structure. And therefore, they say that don't have more than 40%, try to reduce it, or split into 2-3 parts, provide some sort of an expansion joint, flexible joint, so that each segment is less than 40%. After all, there is no problem of sea getting shipped inside. It's far above the deck. So one tries to put some sort of a expansion joint if it is a passenger vessel. If not, then you put it inside. You have a promenade sort of a thing, or you have passage, etc., and you take the continuous wall, say 1.5 to 2 meters inside the two sides. That is the reason. Even if the deck extends like this, you can see in some of these passengers vessels, maybe 1 or 2 decks they have given in line with this side shell, but remaining of them, it is only the curtain plate. The deck is extending, but it is being supported somewhere inset here, and you are giving some sitting space or moving spaces for the passengers and open space there. So you are getting rid of this definition, and you are structurally changing the arrangement. And as far as the length is concerned, you try to give some sort of an expansion joint, which sometimes looks like this. You can have some sort of soft material, which can be a packing material here. So expansion joint above the deck level, if you don't want to increase the height. Okay. So this is how we try to change the stress. Now, if this is the case, then how the stress will vary? If we take the section here and say that this is the neutral axis, this is the keel point K, this is the deck point D, the stress varies something like this. It is linear. So this is the variation. If you consider the top is tension, then the bottom is compression in the opposite direction. So bending stress is always we consider to be linear, and at the neutral axis it is going to be 0. Now many a times what happens that it is not possible to have very thick plates, and this stress, the limiting stress which we consider, may be up to here, and then we say that beyond this let us use high tensile steel. You can still use in the core as mild steel, but where higher strength is required, you can go for high tensile steel. So from here one can say that because the high tensile steel will have a higher limit. So this analysis is required so that you can make an assessment that which portions of the structure can be of high tensile steel. After all, that is much more expensive than the ordinary mild steel. There is no point unnecessarily using mild steel for the entire region where the stress level is not going to exceed the permissible stress limit of mild steel itself. So only where you expect, normally in tankers, very large tankers where the depth is very high, one can go for the deck and the keel construction, the high tensile steel, but the remaining part of the hull and internal arrangement can still continue to be the mild steel. Okay. Now coming to the transverse stress. Now for the shear stress. Now for the shear stress, let us try to draw a block and try to see that how this will behave. Let us take a section here and another section here, A and B. A is at x, B is at x plus dx. That means the distance between these two is dx. And from the neutral axis, this is the neutral axis position I have drawn here, some distance away, which is say y, you take a small layer of thickness dy, and let us see what is the state of stress. Now, here we can assume that the stress is sigma, here the stress is sigma plus d sigma by dx into dx. Now, this sigma and d sigma is created because of the bending moment which is being applied here. On this side is m, this side is m plus dm by dx. Okay. Now, this has to be in equilibrium. Indeed, it is in equilibrium. Now, what is the net force which is acting onto this slice here? So, you have on one side sigma into the depth here, which I can say is the width of the cross section, which is b. So, you have sigma into b on this side acting on a slice of dy. So, b into dy is the area in which the normal stress sigma is acting. So, this is the force in the left hand direction, and the force in the right hand direction is sigma plus d sigma by dx into dx, and the same cross sectional area. Pardon? On this side, the force is in this direction. So, what is this force? Stress into the area. Now, what is this area? If I consider that the thickness here is dy and this is extending in this direction to b. So, b into dy is the elemental area on which this sigma is acting. On the other side, on the same area, we have a stress which is sigma plus delta sigma by del x into dx. Under the action of this, there will be some net force acting. Now, this is I am putting negative because it is in the left hand direction, this is acting on the right hand in the positive direction, so positive. So, these, if you try to find out, this value will be d sigma by dx into dx b into dy. This b into dy I can say dA also for the time being. Now, that means there is a net force acting in this direction, and if you try to sum up all the such forces and different slices away from this particular level, then there will be a lot of force which will be acting in this surface here. Now, what is that force? That force will be, you have to integrate this d sigma by dx, and this has to be integrated. If I say that this is y and this is y max here, ym let me say, so from y to ym. This amount of force will try to pull away from this cross section at this level. That means at this interface, some stabilizing force must be getting generated, and that action is this action, which is nothing but the shearing action. And this shear force must be generated here. That means there must be some shear stress which will be generating at this interface. Now, that interface area is dx into b. And what is that stress? Let me say that stress is tau at that level. This must balance this here. Now, let us see what is this here. Now sigma is m by I by y, and therefore d sigma by dx is nothing but d by dx of m by I by y. Now I is constant of that particular material, and y we have assumed at a particular layer. Okay? So y location is also fixed. So it is only m which is varying with respect to x, and therefore this will be dm by dx. You can say y by I. What is this quantity dm by dx? If you remember this diagram, then on integration of this we have got this. So integration of the shear force is the bending moment, and therefore differentiation of bending moment is nothing but shear force, right. So at that cross section, this dm by dx is nothing but the shear force V or F, whatever you notation you use, and this is y by I. Okay. So if we substitute this value here, then what do we get? We get V y by I B dy dx here, integration from y to y max, and this is tau b into dx. Okay. Now what is b into dy from here to here? B into y into dy. B into y into dy. B into dy is the elemental area, and it is located at a distance y. So what you are trying to do is, you are trying to find out the moment of this elemental area about the neutral axis, and such moments you are trying to sum up from y to ym. Okay. So we can designate by some quantity m, which is y to ym by dy. If you replace this in this expression here, then this will reduce to v by I m dx is equal to tau into b into dx. Dx we eliminate from both the sides, and what we get, an expression for tau which will be given by tau is equal to v by I m by b. This expression gives you the variation of shear stress across the depth of the structure. Now let us try to see here in conjunction with this. Now at this section I said that shear force is given by, let me concentrate to this. Suppose I am considering this maximum shear force position. So this is the shear force which I have with me. Now across that section, if I consider that the section looks like something like this here at that position, then how the shear stress will vary. Now look into this expression. What does it say? This is the value of V. Okay. This I am getting from this section here, right. This moment, neutral axis is here, all that material which is taking that, I am trying to find out all this cross sectional areas moment from here to here if my position is at this position here, y to y max. Okay. So if I am considering the stress here, then from here to here I have to integrate, find out the first moment of this area, right. So this will be maximum at this level, at the neutral axis. If you integrate from here to here, then only it will be maximum. If you integrate from here to here, it is 0. if you take the value at the deck itself, then it is 0. Okay. Then divided by B, B is the width of the cross section. Now what happens? If you take the deck, this is the cross section. If you take the sides, then this is the cross section plus this is the thickness. B is only the contribution from this. Now let us come to this part. As soon as you are here, the shear stress will be very high value, but when you come to this part, the shear stress will drop down because the width suddenly increases from say twice the thickness to the complete width of the vessel here. So that means the horizontal member is not taking the shear force. This expression says that this becomes too much. Okay? As soon as this increases, this stress comes down drastically. The horizontal member do not contribute in taking the shear stress. Its contribution is negligible. Whereas the vertical members take the maximum shear stress of the loading. That's what I told you earlier, and this expression also tells you the same thing. So what happens that when you are considering the top position here, the bottom position here, the shear stress is 0 there. As you are coming down, you will find that at the neutral axis it attains the maximum value by virtue of this M becoming the largest at the neutral axis. As you go away from the neutral axis, once again the value reduces. If you just take a rectangular cross section and try to find out how does the shear stress varies, it will be a parabolic distribution. Having a maximum value at the neutral axis. If you consider a T section, just for illustration, in fact what you can do is you can take a small example and try to solve it. Let me use a different color to show. So this is a part of parabola here, because this is also a rectangular section. It's just a part of parabola, but the width is very high. Then suddenly the width decreases here. So it shoots up. And then this is constant. So the area moment, or moment of this area, do not increase much. It becomes maximum here. And then it drops down to this side. And then suddenly the thickness changes and there is a sharp drop here, and then once again it follows a parabolic path. Okay. So up to this, if you have any questions, I think you can ask me. This is very important. That's why I said that right in the beginning, if you take the total shear force divided by the shear area, what you get is the average. And when we say the average, then this is what is tau average, and this is what is your tau max. Okay, so one gets misled by finding out the average value. It's quite a lot here. In such sections you will find that the maximum is 50% more than the average value. So if your calculations are based on the average value, maybe that the structure will fail in shear, because we might not give this much of factor of safety there. Okay. Of course, for this it's not very critical, and we say that. That is why it is very easy to say that only the vertical members, carry the shear. So here we can coolly say that the contribution towards the shear is from this part. This much of force is hardly anything compared to this entire area. Any questions here? No? So should we take up how to calculate the moment of inertia of this cross section? I once again keep this figure in mind, or I think I will try to draw it separately here, that will be better. This time I am drawing only half the section for the structure. These notations, these are the seam marks, and this is the keel strake from here to here, and then the other strakes are coming. This is the bill strake and so on and so forth, and the last one is the shear strake here. So we do the calculation for INA. So INA calculation. For a given section in a tabular form, and the table will try to put the headings and see that how we try to put it. We put the columns here, column number, some operations here, and then we say the units also. We usually give the serial number for materials in this direction. So let us say that we are taking column number 1. Now what will come in column number 1? In column number 1, we would like to put the scantling items, the name of the item. Say serial number 1, I start with the keel here and I put keel.
The second one is station number.
Serial number. Serial number going downwards. Units is horizontal and column number is also horizontal. Yeah. In the second column, I try to give the scantlings here. Now usually the scantlings are given either in millimeter by millimeter or centimeter by centimeter or centimeter millimeter combination. So let me put here say millimeter by millimeter. Third one, because we have to calculate the moment, and therefore I put lever here, and usually it is in meters. Fourth, now we try to find out what is the area. Area means area of that material cross section, and usual units is centimeter square. Next column we prepare for finding out the first moment of the area about some reference axis. I will come to the reference axis. What is the reference axis? The basic idea is I have to find out the second moment of area about its neutral axis, and therefore the neutral axis have to be evaluated first. I do not know where it is. So I must have some reference axis about which I do all the calculation and then arrive at the neutral axis. So this is the first moment of area I will write. And then in the next one, I say it is the second moment of area. And then another column I add, and I say own moment of inertia. Own moment of inertia. And then it is the total moment of inertia of that about the reference axis. Okay. Now, where is the reference axis? We have seen the diagram and we see this structure here. We say that the neutral axis will be below the mid depth. Now, if for example, if we say that the depth of the vessel is say 9.5 meters and mid depth is 4.75 meter, we can consider that the assumed neutral axis is some round figure of that below 4.75, maybe 4.5 meters or 4 meters, but still we have to do a calculation. So if we assume say 4.5 meters from the keel is the assumed neutral axis, then above that whatever area is there, I consider it to be positive, having a positive lever, and anything below it must have a negative lever values. Now this positive and negative one has to keep in his mind, and accordingly you have to find out all this. Now the second moment of area, there is no problem because you are multiplying by the same quantity twice, so positive is positive, positive negative is positive, but the first moment depending on positive or negative will change. And there are a number of such items. If you just consider here, I think it will go into a big list of about 100 items. And for each, because we are seeing that all this may be of the same profile, but the cross section as it is, the things will change because you may have camber, you may have this rise of flow and so on and so forth. So they are not at the same level. The stiffener may be identical, but their lever will keep on changing. Okay. So the best will be to get out of this confusion that we can assume that at the keel level we use the reference axis. So we can say reference axis is at base or keel or whatever it is. So no ambiguity regarding plus or minus here. Everything is positive. Okay. Now let us see what is the keel. Now keel plate is one single plate. We are considering only half the section. The other half is mirror image of it. So we do half the calculation, multiply it by 2, we get for the entire section. Now keel, center girder, etc. may create some trouble, and therefore one has to be very careful and put that half right in the beginning and say that the dimension is maybe that the keel plate width is 1400 millimeter, thickness is 20 millimeter. So I write 1400 by 20. I have already said millimeter by millimeter. So I give 1400 millimeter by 20 millimeter. What is the lever? If it is 20 millimeter, then it should be 10 millimeter below the keel. Okay. Now when I am talking about the ship's depth of 9.5 meters, with respect to that 10 millimeter is absolutely negligible. It is not going to affect my calculation, and therefore it is not 0, so I do not write 0, I just put a dash here. Okay. Second item I take, say this is strake A, strake B, this may be the bilge and so on and so forth. I put A strake. I write say 1600 by 18 millimeter, and this lever is also 0 because I am considering it to be a flat bottom shape. So, like that everything will be flat here till you come to say item number 5, bilge strake. You have these values and this value also will be something here. Putting dot 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 means some value is there. Okay. Then you come to say item number 6, bilge is put say D, E, F, etc. So, you put all these strakes, D strake, 7, E strake. Like that one completes all the outer hull part. Then you can come to the inner bottom, finish all those strakes there. Then you come to these plate items, center girder, side girder, etc. Okay? Center girder, side girder, deck girder, etc. Then you come to all these longitudinals, and like that one tries to enlist everything and complete this part of the table. Get it checked by one of your colleagues so that you have not missed out anything, because if something goes wrong it will be only carried over. You cannot rectify later on. So, at stage by stage one has to do the checking. All this has been done, then you can calculate these values, there is no problem. This here will be 0, 0, or I am simply ignoring, but all these values will be there. Now, all the areas have to be summed up and I call it sigma A. All the first moment have to be summed up, I call it sigma M. All the second moment has to be summed up. It is only for checking this sigma and this sigma is required, but I only try to find out what is sigma I here. These two added up together should give me sigma I. So, this is only for the checking part, but what I require is sigma A, sigma M and sigma I. Okay. Now, here I have taken this reference and INA will be somewhere here, and this will become my YK, Y of the keel, and this becomes Y for the deck. Now, after finding out these summations, I can write YK is equal to sigma M by sigma A. Okay. And I can find out YD from deckhead side, this height plus camber minus YK. The depth of the vessel is measured at deckhead side, from the keel level to the deckhead side, and the stresses will be maximum at the extreme skin on the deck, which happens to be at the crown of the deck, that is at the center line. There you have the maximum camber. So, D plus C, C may be 0 if you are having a flat deck, but usually you have some camber. So, let me put it, camber can be 0, so I put this equation here. So, I get what is YK, I also get what is YD. Now, INA, neutral axis, will be sigma I minus total area into YK square. This is the parallel axis theorem. So, the moment of inertia about its own neutral axis will have a minimum value about the reference axis, whatever is there, minus the total area multiplied by the distance square. It's okay. So, I get what is INA, and now after getting this INA, I try to find out what is the section modulus minimum for the deck. The notation for section modulus is Z, and Z is nothing but I by y. So, if I say that z for the deck will be INA by y deck and z for the keel will be INA by y keel. Now, after getting these z values, I can find out sigma at deck is equal to m by z deck and sigma at keel is equal to m by z keel. It's okay. So, these two gives me the numerical value at any section, but usually what we find that the maximum bending moment occurs somewhere near the midship section, and at the midship section I have the section because I draw that detailed drawing for my class approval, and usually a ship has got a parallel middle length, and if you see the maximum position of the bending moment, it will be in the parallel middle length. So, calling it to be say I midship is not erroneous because the same section goes on for a particular distance around the midship region, which I have for my class approval, and my maximum bending moment will be somewhere near the midship region. Okay. And therefore, if I call this to be say maximum here, then these are the maximum stresses, and if the deck is, if it is a hogging condition, deck will be in tension, sigma d will be tensile, sigma k will be compressive. If it is a sagging condition, sigma deck will be a compressive stress, sigma k will be a tensile stress. Fortunately for steel, the permissible limits in tension and compression is identical, but there are materials which do exhibit a different properties under tension and compression. For example, concrete. Concrete is very strong in compression but very poor in tension. So, in such cases one has to find out what is what. Okay. So, other than metal structure, if we try to use any other material, then maybe that this will be of importance. It's okay. Any questions?
So this tabular what we are constructing is for all the members we are calculating?
Yes, we are considering all the members. Basically in a tabular form, if you try to put it, it becomes easier to check in a matrix form whether you have listed all the item or not. And once you have listed all the items, whether the scantlings are given, their positions are given or not.
That means huge number it means.
Yeah, it is a huge calculation. One has to do this calculation. This is for the ship when it is constructed, but for class approval there is another set of calculations, and they are available in the classification society rules. One has to satisfy this value, that value, but you have to do this calculation, otherwise you will not know whether it is going to satisfy that or not. It has to check. That is only a sort of a cross checking. There are certain approximate methods also. I think I will take it up next time. No point hurrying up, then everything will get jumbled up and mixed up. No, this part is fairly simpler part. Today 1 hour class. I said that 1 hour class today.
We'll dress up also because we have studied these things.
Yeah.
But maybe 15 years back. For him, maybe around 25 years.
No, but he is a teacher already. So his colleagues must be talking about such things.
Which book to refer for this, sir?
Unfortunately, there is no latest book on this. So, what we try to do is that different portions we have taken from different textbooks, sort of a thing, and then we have tried to give a latest flavor to this. We used to have a book by Muckle long back, but Muckle died, and after that nobody has revised his edition. And we were fortunate that Makal also came to this campus and he has delivered lectures here also. Yeah.
Which year was that?
Huh?
Which year was that?
Most probably 1975. Because his direct student was our head of the department, so he requested him once that why don't you visit India? So he said, okay, I'll come to India. So I went to the station to receive him. He was an old man at that time. And he came, he gave a lecture. And unfortunately, that book is not revised, and after that, lot has changed. In fact, after 78, when the fuel crisis was there, the Suez Canal was closed, the ship sizes increased, and a dramatic change took in the shipbuilding and shipping field, totally. The size blew up like anything, and once the size grows, then the economics will be different, and the design features changed. Before that, only 3 types of conventional vessel, either a ore carrier or a grain ore or grain. That was the type of bulk carrier in those days, and general cargo carrier and tanker. There was no third variety. Container was much later. Before that came the variety of tankers, and tankers in those days was only crude carrier, either crude or vegetable oil or water tanker, nothing more than that. And then after that started coming this product tankers, chemical tankers, and perishable goods tanker, and so on, refrigerated tankers. And to take into account all those things, definitely the rules cannot cover all the things. Something is being taken in, say, high pressurized, low temperature condition. Something else is taken in heated condition. Something else is taken in a cryogenic condition. Outside ambient temperature is 30 degrees and inside temperature is, say, minus 40 degrees centigrade. And this is the thickness you are having. Can you have it or not? You have a corrosive material, highly corrosive inside, say acid you are taking. Outside is also corrosive but not that severe. Now how are you going to carry it? Hazardous material. So totally the things changed. When it was a coal-fired steam engines, then machinery was at midship. When the diesel engine, they again conservative, you put it at the midship, otherwise there will be heavy trim. But then they started shifting it slowly and slowly. Today you don't see any ship which has got a hole behind the engine room. Engine room is the last.
You come across such ships?
No, that must be old. Or a very new concept where you put it in the forward region.